Now that you can load and plot two-dimensional images, let's discuss higher dimensional datasets. Images come in all shapes and sizes. This makes them versatile, but also complex. A standard grayscale image is the simplest type. It's an array that can be indexed by rows and columns. 3D images cover a volume of space rather than just a single plane. This volumetric data is useful because it can better capture the complexities of the human body, but it can be difficult to visualize because it can't be summarized in a single plot. Color images are also three-dimensional. RGB images, for example, have 3 color channels that, when rendered by Matplotlib or other image viewers, express a wide range of colors. Movies or time series data include a temporal dimension, showing how each element changes over time. Like the planar dimension for 3D volumes, the temporal dimension is put first by convention. Just as a 2D image is a stack of one-dimensional vectors, 3D, 4D, and even higher dimensional images can be thought of as stacks of simpler ones. Let's illustrate this by creating a 3D volume from a few 2D images. First, we'll load ImageIO and NumPy. Then, we'll read in 3 slices of a chest CT scan. Each of these slices is an array with 512 row elements by 512 column elements. Now, we can feed a list of these 3 images into NumPy's stack function to create a 3D volume. If we look at our new vol array, we see that it contains a third dimension with 3 elements along it, but the row and column dimensions are the same as before. ImageIO's volRead function is capable of reading volumes directly from disk, whether your images are stored in their own folder or if the dataset is already multidimensional. In this example, we have a folder named chest data, which contains 50 slices of a 3D volume. We simply have to pass the folder name to volRead, and it will assemble the volume for us. Since these are DICOM images, the function actually checks the available metadata to make sure that the images are placed in the correct order. Otherwise, it will default to alphabetical order. Displaying the shape attribute shows us that we have 50 images stacked together. When analyzing images, keep in mind that the data is only a representation of real physical space. The information in your images is limited to the number of elements in it. This is known as the array shape in NumPy and is always available as an attribute. The amount of space covered by each element is the sampling rate, and it can vary along each dimension. For DICOM images, the sampling rate is usually encoded in the metadata. For other types of image formats, such as JPEG and PNG, you may need to find it elsewhere. The field of view is the total amount of space covered along each axis. It is the product of the shape and sampling rate. Understanding the difference between these concepts is important, and we'll return to it throughout this course. Now, let's start exploring some 3D volumes. Efficiently and comprehensively visualizing your data is key to successful image analysis. Consider this loaf of bread. It's a 3D volume that looks absolutely delicious. But what's inside the loaf? Is it bananas, blueberries, walnuts? This single 2D image cannot answer the question. Instead, you would have to slice it up and look at those pieces individually. The concept for 3D images is exactly the same. To explore your multidimensional array, you must visualize many simpler slices of it. It's inefficient to plot each of these slices one by one. A better way is to display many at once. To do this, we'll leverage PyPlot's subplots function, which creates a grid of axis objects based on the number of rows and columns you specify. When you call pyplot.subplots, it returns a figure object and an array of axis handles. In this case, the axes array has a shape of 1 by 3. To draw images on each subplot, we will call the imshow function directly from the axis object, rather than calling it through pyplot. Here, we're plotting the first slice of vol with a gray color map. After the first slice is drawn, repeat the process for the other slices. Finally, we can clean up and render the figure. Just like before, we want to turn off the ticks and labels by calling the axis method. However, since we will do the same thing to each subplot, a for loop is more efficient than writing down each command. If you had many images to draw, you could insert the drawing step into a for loop as well. Finally, we render the image using pyplot.show, and we are greeted with a nice set of images that move sequentially through the chest volume. There are actually multiple ways you can slice a 3D volume into 2D images. The simplest way is to choose a frame along the first dimension and plot the second and third against each other. If you instead selected a slice along the row dimension, you would get a second perspective. In this case, we are plotting head to toe versus left to right. Finally, you could plot the first and second axes against each other, yielding a third view. When looking at human anatomy, these different views have special names: the axial, coronal, and sagittal planes. Knowing in which plane a dataset is stacked can help you navigate more efficiently. Many datasets do not have equal sampling rates across all dimensions. In these cases, you will want to stretch the pixels along one side to account for the differences. The amount of stretching needed is determined by the aspect ratio. Here, we've decided to plot a slice with data from the first and second dimensions. To determine the aspect ratio, we first get the sampling rates along each dimension from the metadata dictionary. Then, we divide the sampling rate of the first dimension by the sampling rate of the second. When we call imshow, we pass this ratio to the aspect argument. This results in a properly proportioned image. Failing to adjust the aspect would have resulted in a distorted image. Now, let's practice using these techniques to plot 3D images.